Hi everyone, welcome back. In this lesson, I'll introduce all the rules for proof trees for propositional logic. In the last lesson, I introduced the idea of proof trees and explained why they can help with analysing logical relationships, especially in cases where truth tables get too big. Truth trees are a smarter way of finding evaluations. You interpret formulas from the outside in, rather than evaluating propositions by listing all of the possible values of the atoms. That works well enough in simple cases, but when you have lots of atomic formulas, exponential growth makes listing them all a dumb way of doing things. In the next lesson, we'll see examples of truth trees, but in this lesson, I'll be presenting the rules. Nothing more, nothing less. This won't be the most interesting lesson you have, but it's a lesson you'll probably want to refer back to a few times as you work on trees yourself. The motivating idea with trees is that we write down formulas and work out what else would be involved if those formulas were true. Sometimes we get more formulas that straightforwardly follow and we write them below our starting formulas. So I might start with a bunch of formulas and then processing these, write down some new formulas. And sometimes we have options and the tree splits into branches, and I might have a formula here and some formulas here, and I get more options like this. Some of these branches close because the requirements that they have are inconsistent. But sometimes some branches might not close, they might stay open. And if when you end you get a branch that doesn't close, this whole branch of the truth tree describes a way to make the starting formulas true together. If there isn't such a way, these formulas can't be true together. So, here are the rules. If we have a conjunction, we simply unpack it into its conjuncts. If A and B is true, then so are A and B. And you'll notice this works in reverse. If A and B are both true, so is the formula we started out with, the conjunction A and B. This tells us what would happen if a conjunction is true. What about if a conjunction is false? Now remember, every formula we write down is one we're taking to be true. So to say that a conjunction is false, we write down its negation. Here, it's not the case that A and B. If a negated conjunction is true, then A and B is false, which means that at least one of A and B are false. So we branch with two options. One for not A, saying that A is false, and the other for not B. If a disjunction A or B is true, then one, at least, of its disjunctions, A and B, is true. So again, we have two branches, one for A and one for B. Now it's worth explaining why this rule has got two branches and not three, when A or B is true in 3 rows of a truth table. So if you have the truth table for A and B, we have these 4 different rows, and the disjunction is true in 3 of them. So it looks like I've got 3 different options for a disjunction A or B. And indeed, I could have a rule with 3 branches, which goes like this. A or B, one option has A true and B true. One option has A true and B false, and another option has A false and B true. And this rule would correspond quite nicely to the truth table that we have here, because I have 3 different rows corresponding to the 3 different branches. But this rule is more complex than it needs to be. Our original rule here has the same effect. The left branch says that A is true, and B could be either true or false. That corresponds with both of these branches of my 3-branch rule. The right branch here, B, says that B is true and that A could be either true or false. And that corresponds to, again, the first branch and this last branch of the 3-branch rule. So the rule that we have here for A or B is simpler, and that's the one that we're going to go with. Now, if a negated disjunction, it's not the case that A or B is true, then A or B is false, which means that both A and B are false, so we write down both not A and not B in the one branch. A conditional is sort of like a disjunction. For a conditional to be true, it isn't false, which means we don't have A true and B false. So we either have A false, that's the not A branch, or we have B true, and that's the B branch. A negated conditional, it's not the case that A implies B, is true. That means that A is true and B is false. So we write down both A and not B in the one branch. If a biconditional A if and only if B is true, then A and B have the same truth value, which means we have two options. One branch containing A and B, and the other containing not A and not B. And if a negated biconditional, A if and only if B is false, if a biconditional A if and only if B is false, if its negation is true, then A and B have different truth values. There are two options, one branch containing A and not B, and the other containing not A and B. Now these are all of the binary connectives, both in positive and negative form. Now it's not all of the shapes that a complex formula can take. There's one case left, the case of a negated negation. If not A is true, then that means that not A is false, and it follows that A is true. So we simplify a double negation by deleting the two negations. And that completes the connective rules. The final rule that we have is the closure rule. If a formula A and its negation not A both occur in the same branch, then that branch closes, and we indicate closure with a little cross, like this. So let's pause for a moment and check that you've understood how these rules work. Suppose we have a new connective, which I'll write with a star, where we define A star B as neither A nor B. So a truth table for A star B has got A star B true in the row where A and B are false, and A star B is false otherwise. Which of these three pairs of rules is appropriate for A star B? How did you go? If you've got questions or comments, if you'd like to explore the issues further, take a look at the course notes for this section and head into the discussion boards to follow things up. I'll take a look and see how you're going. Now, here are some words and concepts that we use when talking about trees. A branch of a tree is closed when it contains a formula and its negation, and it's open if it isn't closed. A partially developed tree for a set of formulas, and the notation that I'll use when I'm talking about a collection of formulas is this Greek letter sigma. So, a partially developed tree for a set sigma of formulas is a proof tree starting with the formulas in sigma, in which each formula in the tree is either in the starting set sigma or follows from formulas higher up in the tree by way of the rules. A completed tree is a partially developed tree in which each complex formula in each open branch has been developed. And we write sigma with a single bar turnstile to say that a tree for sigma closes. It means that the set sigma is inconsistent. And we write sigma turnstile A for sigma and not A with a turnstile, because this is the tree we'd use to check if the argument from sigma to A is valid. For the argument to be valid, we need there to be no way where the premises are true and the conclusion false. If the tree for the premises and the negation of the conclusion closes, that's exactly what it shows. So we say sigma turnstile A in exactly this case, when the tree for sigma and not A closes. This closed tree represents a proof from sigma to A. Now that's it for tree rules. In the next lesson, I'll work through some examples so you can get a good idea of how the rules are applied.